I'm Hunter,
Hi, I'm Pierre-Alain.
and we're going to be presenting on iron, nickel, and our alloy Invar. So for this project, we're going to discuss the mechanical properties of iron and nickel, in particular things like the elastic modulus, yield strength from field points, tensile strength, facts about ductility and resistance and toughness, as well as an example where we apply these principles. So for the first question, we talk about the elastic modulus, which we calculate using the slope of this line within the elastic region, which is going to be calculated using rise over 1 or sigma over epsilon. For pure iron, we're going to use that formula. We are going to create two lines that will intersect the line that we chose, which is as close to room temperature as we could get. For those, our stress is 7 gigapascals and our strain is going to be 0.05%, which creates a Young's modulus or elastic modulus of 140 gigapascals. So for pure nickel, we're going to take the same approach. We're going to select our line as close to room temperature as possible and drop our two lines. The stress that we've chosen is 6 gigapascals and the strain we've chosen is 0.05%. Once again, we're just going to plug that into our equation and derive 120 gigapascals. So Invar is our alloy. Once again, we're just going to take that same approach. We've got our formula, which is our elastic modulus, sigma over epsilon. The point we've chosen is 600 megapascals as what we've estimated to be 0.005% strain. Once we plug that into our equation, we get 120 gigapascals for our elastic modulus. All right. So for question 2, we're going to be calculating the yield strength for each of these materials. So the yield point is going to be the point that separates the elastic from the plastic region, as you can see on this graph. In engineering practice, we're just going to take a parallel line to this elastic region that runs through the 0.02% strength and find where that point intersects this line. So for iron, I've drawn an exaggerated dotted line that represents that parallel line that we use in engineering practice. And you can see where it would intersect. That's where we would call the yield point. And for iron, that yield point is 230 megapascals. Roughly. For nickel, we take the same approach. Again, it's very exaggerated, but you see the offsets, and we're going to take the point at which it intersects. For nickel, this is going to be roughly 70 megapascals. And then once again, same approach for Invar. We take our offset, we're going to find the points at which they intersect. And for Invar, that is going to be roughly 310 megapascals.
So, we're good?
Yeah.
So we're going to be talking about tensile strength now. Tensile strength, or ultimate strength in this diagram, would be just the maximum stress that a material can endure, which will occur right around here at the topmost point. So for pure iron, it would roughly be 414 megapascals. For nickel, 317 megapascals, and for Invar, around 445 megapascals. That's their typical tensile strength. So we're going to talk about ductility, which comes down to two parts: percent elongation, which is described using this formula. Length final minus length initial, all over length initial, multiplied by 100, and percent area reduction, which uses the following formula: area initial minus area final, all over area initial multiplied by 100. So we're going to talk about resilience right now. Resilience is just the ability for, it's just like how much energy a material can yield, or like how much energy a material can store. And typically you would calculate or find it by taking the integral of the elastic region. In this case, we're just going to approximate it by taking the area underneath this curve, which would be 1/2 rise or stress by run strain, which would give us 1/2 multiplied by 8 gigapascals times 0.06, which gives us roughly 240 megapascals as a result. To calculate resilience for nickel, same process, area underneath curve integral. In this case, 1/2 rise 12 gigapascals by run 0.01, which would give us a resilience of 0.6 gigapascals. And finally for Invar, we are estimating a lot here. Integral, again, underneath the curve. In this case, we're estimating 1/2 600 megapascals by 0.005, which would give us a resistance of 1.5 megapascals.
So, the toughness. The toughness can be defined as the energy needed to break a unit volume of material. In that case, the toughness can be approximated as the total area under the stress strain curve. It has that equation right here. And here we gave you the example of the stress strain curve for pure iron, for nickel, and for invar. So for question 7, we have a special example where we have a cylinder of our specimen metal 1, which is iron, and metal 2, which is nickel. We asked to find the change in length and change in width. So the formula that we use are all there. At first, we have the Young's modulus, which is equal to the stress divided by the strain. And the stress is equal to the force divided by the area, and the strain is equal to the change in length divided by the original length. So from those formulas, we can get to this one, which is F divided by A multiplied by the original length divided by the change in length this time. But because we're looking for the change in length, we're gonna end up with this formula, which is change in length equal force times original length divided by the Young's modulus times the area. So for the change in length, as we add that formula, force times original length divided by Young's modulus times the area, we plug in the numbers where the force is 4 kilonewton. The original length was given as 1 meter. Our Young's modulus for the iron is 140 gigapascal, and the area is pi r squared, with our radius here being 10 centimeter. And we found that result here, 9.09 times 10 to the minus 7 meter. So, same thing to find the change in length of the nickel. We just have that same formula, and we just plug in the number. The force is still 4 kilonewton. The original length is still 1 meter, but the Young's modulus is different. It is 120 gigapascal in this case, and the radius is still 10 centimeters squared. So we end up with those numbers, 10.6 times 10 to the minus 7 meter, which is 1060 nanometer for the change in length of the nickel. So now we're trying to find the change in width. So for the change in width, we're gonna need the Poisson ratio. So we're gonna use this equation that gives us the lateral strain is equal negative the Poisson's ratio times the strain. But we also know that the lateral strain is equal negative width, negative the change of width, divided by the original width. So from that, we can plug in the second equation in the first one. We end up with that equation right here. We're gonna remove the minus. We're gonna have this one where everything is positive. In the meantime, we changed the values of the strain, because let's not forget that the strain is equal to the change in length divided by the original length. So that's what we have here. And because we're looking for the change in width, we're gonna multiply everything by the original width, and that led us to that equation here where we have the Poisson's ratio times the change in length times the original width, all divided by the original length. So now for the change of width of the iron, we already figured out our formula. It's gonna be the change of width equal the Poisson's ratio times the change in length times the original width, all divided by the original length. So now we're gonna plug the numbers. The Poisson's ratio of iron is 0.29, and the change in length we found it here is the same that we plugged in, but the original width was given and it was 20 centimeters. So we're gonna divide it out by the original length that was 1 meter, and we end up with the change of width being 5.27 times 10 to the minus 8 meter. But what we gotta understand is that the width is actually decreasing. So what we found here is the magnitude, but in real life, in engineering life, the width is actually decreasing. So for the nickel, is stays the same formula, but we're gonna plug different numbers. The Poisson ratio of nickel is 0.315, and the change in length is the same that we found here. We plugged it. The original width of our cylinder is still 20 centimeter, and the original length is still 1 meter. When we plug it all, we end up with that number, 66.78 nanometer. It's still, the width is still decreasing. That was the end of our project. Thank you for watching us. I hope that you guys have learned a lot about iron and nickel. So this was Pierre-Alain.
I'm Manfredo.
And Hunter Sanford.
Thanks.